So, again the start of a new lecture. So, we will just review the contents of last lecture briefly and then move on to the new lecture, and this is the last lecture of this module. After that we will have 2 or 3 smaller modules which we should finish in 3 or 4 lectures. So, we are just coming to the end of this course now. So, in the last lecture we discussed about, so just let us say review. So, in the last lecture we talked about basically magnetic ferrites, and as the name suggests itself, since the name is magnetic ferrite, most of these are iron containing compounds, and that comes from the magnetic property of iron. So, the first of these happens to be your spinel ferrites, and these spinel ferrites we discussed were a variety of these Fe3O4, NiFe2O4, ZnFe2O4, etc. And these were also classified as inverse or normal. So, depending upon how the cations distribute themselves in the octahedral and tetrahedral interstices of FCC lattice made by oxygen atoms, these would be called either normal or inverse ferrites. And based on the distribution of these ions in the interstitial sites, you could work out what is the net magnetization, and this magnetization essentially, if you take one site, let us say tetrahedral side up, then octahedral would be down. You can take either of them up or down, but the point is they are opposite to each other, and it is a net magnetic moment of each of these site, and algebraic sum of those two determines what is the net magnetic moment of the material. And as a result, these materials happen to be quite magnetic in nature. They have large magnetic moment, and they are soft materials, which means they have a slim hysteresis loop. So, they are typically soft ferrites. And then we talked about hexagonal ferrites. In the hexagonal ferrites, we were mainly interested in barium ferrite, barium hexaferrite, which is based on on the name magnetoplumbite, and that is why it is called as M-type ferrite as well. Now, this is a hexagonal unit cell. You can talk of this material as if it is BaO dot X Fe2O3, and this essentially happens to be 6 essentially, and this happens to have a mixing of FCC based and HCP based layers. And since FCC HCP packing is fairly similar, except that in FCC you have ABC ABC, in HCP you have AB AB packing, so they mix with each other quite well, and resulting in a structure which is hexagonal in nature. And this material also has a large magnetization, as we discussed upon distribution, based on the distribution of iron atoms, because iron here is the magnetic ion. So, based on the distribution of these iron atoms, you get a net magnetization. This material is highly anisotropic, and as a result it is called as hard magnet. So, this is a hard magnet. And then third case that we took was of garnets, and these garnets are basically based on mineral names, but they are magnetic. Iron containing garnets are magnetic in nature, and these could contain so they are yttrium, or let us say not yttrium. So, they are the compounds containing rare earths or lanthanides, iron and oxygen. So, the general formula for them would be Re3, Fe5 and O12. You can again break them into 2 oxides. So, this is let us say Re3, so it is essentially Re2 O3 1.5, and then what you have Fe2 O3, and then multiply by such a factor so that it becomes 5. So, it is 5 by 2. So, it is essentially, you can see that it is it's 7.5 plus 4.5, that make up 12. So, this is what is essentially garnet is, and garnet can be tuned quite well, because you can use this radium rare earth atom as either yttrium or terbium or gadolinium or neodymium or lanthanum, and depending upon the magnetic strength of each of these ion, you have a net magnetization of the material, and which essentially is nothing but 5 minus 3 mu r into times mu b, or you could write 3 mu r minus 5. So basically you take more of this. So essentially, depending upon the strength mu r, which is the strength of magnetization or magnetic moment of these rare earth ions, you get the net magnetic moment, and this is of course tunable. And again, these structures can be made in single crystal form, they can be made in oriented form. So as a result, microstructural tuning of these materials is quite important in determining the properties of these materials, and also the composition, which determines both the magnetic moment as well as the Curie temperature, or is the temperature of operation, let us say. So this is essentially the summary of what we discussed last time, and what we will now take up is essentially one more thing that we that we sort of did not discuss last time was especially in the case of spinel ferrites. Now, in case of spinel structured ferrites, let us say now the formula, let us say, is MeFe2O4, where M is some metal ion. Now, this metal ion, you can make it look like as if it is NiZnFe2O4. So it is a mixture of nickel and zinc. Now, here you see that nickel is a magnetic ion, but zinc is not a magnetic ion, it has a zero magnetic moment. But by careful mixing of these two, you can achieve a magnetic moment which is actually higher than the parent compound. So the distribution, when you mix zinc in there, the distribution happens to be Fe3 plus 1 minus, let us say, if delta is the level of non-stoichiometry or level of mixing, let us say, then Zn delta, and that is 2 plus, and then Fe1 plus delta 3 plus, and Ni 2 plus 1 minus delta. And the way these ions have distributed themselves is because nickel, so this is nothing but, you can say, NiFe2O4 into ZnFe2 dot ZnFe2O4, and if you look at here, this is 1 minus delta and this is delta. Now, this happens to be a normal spin, inverse spinel, and this happened to be a normal spinel. Here the distribution would be Ni Fe dot Fe04, and so it would be AB2, essentially AB dot BO4, and this would be Zn dot Fe2O4. So here nickel and iron atoms go to A site, which is the tetrahedral site, and nickel and iron atom go to octahedral sites, and one of the iron atom goes to tetrahedral sites, and here zinc goes to tetrahedral sites, and both the iron atoms go to octahedral sites. So when you mix them together, you make sure that iron atoms going to tetrahedral site in nickel ferrite combined with the zinc atoms which go to tetrahedral site. So that is what you see here, that iron and zinc combine with each other going to tetrahedral sites, and nickel and iron combine with each other to go to octahedral sites. So this is octahedral, this is tetrahedral, and that is how you distribute these ions with respect to each other. Now, here the beauty is when you calculate now it is fairly straightforward to calculate the net magnetization. You just have to use the values of iron, nickel and zinc and multiply them by 1 minus delta and 1 plus delta, wherever is applicable. Now, the beauty of this is that when you plot this magnetic moment versus percentage versus delta, now this magnetic moment versus delta, so let us say if this end is nickel ferrite and if this end is zinc ferrite, and this delta is the level of doping or level of mixing, and then what you see is that, so this is mu at 0K. So this goes through a maxima, something like this, and this maxima occurs at around roughly 0.4. So it's around 0.4 you get a maxima in the magnetization, and this is, and after that then again it decreases, and then of course you go to Zn Fe2O4, where zinc has zero magnetization. All the magnetization comes because of Fe atoms. So this is how it looks like, and it becomes 0 for Zn Fe2O4. And another thing that we discuss here is the addition of essentially non-magnetic ferrite to a magnetic ferrite in spinel structures, of course, and this is quite important and interesting as well. Now consider NiFe2O4. Now NiFe2O4 is the inverse spinel, and whose magnetic moment you can calculate, and this is 16 mu b per unit cell, or you can say that in one unit cell you have 8 formula units, so 2 mu b per formula units. Then we talk about zinc ferrite ZnFe2O4, which has 0 magnetic moment, 0 mu b, and this is again inverse structure. Now typically you would believe, just by using the rule of mixtures, that if you mix these two together you would get decreased magnetic moment, but no, that is not true. When you mix nickel Fe2O4 and ZnFe2O4 together, then the side structure that they create is, so you have Fe1 minus delta, Zn delta into Fe1 plus delta, nickel 1 minus delta O4. This is the kind of structure that it makes, and when you now work out the magnetic moment of this oxide's magnetic moment, when you plot here, so it goes up to a maxima at around 0.4 of delta, and then it decreases again. So by mixing of a non-magnetic oxide, because the structure goes through essentially a redistribution, although both of them happen to be inverse in the pure form, when you mix them together it becomes a mixture of pure and it becomes a mixture of inverse and normal oxide, spinel oxide. So what happens here is, essentially if you look here, these go to octahedral site and these go to tetrahedral site, and as a result you have mu up and mu down, and this gives rise to a non-zero magnetic moment which is higher than the parent compounds. So as a result you get about 40% at the doping level of 40%, you get about you get a higher magnetization, which you can calculate depending upon by putting in the value of delta as 0.4. So this is the exercise, which is fairly simple exercise to perform, and the point here to illustrate is essentially that the site exchange or site occupancy by these cations can result in a much more improved performance of these ferrites. And the commercially important ferrites in many applications, as we will see later on, are manganese zinc ferrites, and you will see that zinc comes quite a lot, and then nickel zinc ferrites, and this is dependent upon the different properties of these two ferrites, which we will discuss, which we will put into a context later on. Okay, so now the thing that we are going to discuss is another thing about garnets is that garnets are compositionally tunable. So as a result, when you make a plot of the magnetic moment versus temperature, then you for variety of materials, for instance, it changes the Curie temperature or the temperature window of operation, it changes like this. So for instance, if this is the window for yttrium, let us say this is the window for holonium, and this could be sorry, this could be window for erbium, this could be window for polonium, etc. So gadolinium will give you a window like this. So depending upon the element you put, its temperature window of operation during which the magnetization is more stable can be obtained. So for instance, if you take a YGD-FeO compound, which means yttrium and gallium substitute for each other, so 3Fe5O12, then for certain concentrations, so if you take for x is equal to 0, which is your GD is equal to 0, then you get a window like this, and magnetization temperature of about 280 degrees centigrade Curie temperature. And if you go for instance 0.3 and 0.4, you get something like this. So depending upon the composition, you get a temperature window of operation for these garnets. So this, which is compositionally tunable. Also these garnets can be fabricated in various forms. They can be formed in single crystal form. They can also be formed in tape form or oriented ceramics, and as a result of some magnetic anisotropy, this changes the magnetic properties of these ceramics. So now what we will do is that we will shift our attention now towards the properties of these magnetic ferrites which affect their magnetic behavior. So we will now look at the properties of importance for ferrites. Okay. So first is the case of, let's say, soft ferrites, and soft ferrites are typically your cubic spinel ferrites, and here they are used in applications like inductor cores, or also called as pot cores, for telecommunications, they are also used in low power transformers and high flux transformers, and you can also have television line output transformers, and many applications you can use them for. If you want to go into detail about the applications, you can go through the book of electroceramics as a reference reading by Moulson and Herbert, and this is Wiley publication. So this is an excellent book for talking about variety of applications. So this is a nice book as a reference reading. So one of the properties of importance is permeability. Mu r. Okay, and this mu r is dependent upon things like composition. Composition is one of the important factors which determines this, and another is microstructure. How the grains are, what is the grain size, what is the level of porosity, etc., which determines this. And it's not a very straightforward to determine this, but it depends upon various magnetic parameters as well. So magnetic parameters such as your saturation magnetization, MS, and then or let us say high MS, low magnetic anisotropy, and low magnetostriction. Magnetostriction is essentially the coupling of magnetic and elastic properties. and which is low in these materials. So, so essentially this permeability depends in a quite complex manner on high saturation magnetization, low magnetic anisotropy and low magnetization. Typically the magnetic anisotropy falls off quite rapidly as the saturation magnetization falls to a low value near the Curie temperature, because as you know, as you increase the temperature to Curie temperature, the saturation magnetization decreases. So as a result, this magnetic anisotropy decreases, which is understandable because of thermal forces becoming dominant, and as a result you have a low permeability of these materials. Now in case of nickel Zn ferrites, this magnetic anisotropy is low, and this can be adjusted by, basically it can be tunable by substituting small amounts of cobalt by cobalt substituting to nickel. So this cobalt is a very important element in tuning the composition of magnetic ferrites, and here it can change the anisotropy behavior of these nickel ferrites by cobalt addition. Now another thing which is important is the sintering atmosphere. Sintering atmosphere can affect your magnetostruction properties, but it can also microstruct. So you can have effect of sintering. Now sintering, as you know, is a densification process, and this densification process, the way you carry out, what temperature, what atmosphere, what time, this determines the densification of the ceramic, and this densification essentially controls the microstructure. Microstructure will mean grain size, porosity, grain size would mean grain boundary as well, and the type of grain boundaries, whether they are insulating, whether they are conducting, etc. So essentially this makes a dominant contribution to your domain walls, or dominant effect on the domain walls, the way they move, and that is how you change this, and this has a dominant effect on mu r. So essentially if you have a microstructure which leads to pinning of domain walls, then, or if you have kind of porosity, then this sort of reduces the permeability of the material. I'll show you some of the effects of this. So for instance, so if you look at, for example, in some system, the variation of mu as a function of grain size, the model system, then it increases as you increases the grain size from, let's say, 10 micron to something like 30 microns, and this increase in permeability can be 2 to 3 times. So this is the effect of grain size, and then you can also do it by, you can also study the effect of change of fractional porosity. So porosity also has a dominant effect. So so it sort of tends to reduce the permeability of ferrite materials. So both grain size and porosity are function of the way material is made, and this has a profound effect on the properties, especially the permeability of ceramics. Another thing that is of importance is the loss factor. Loss factor is, you know, is nothing but tan delta, and this tan delta has contributions from various sources, and the sources could be, you know, your hysteresis sources, it could be eddy current losses, and it could be just the residual losses, and these residual losses are not easy to quantify or identify, but they are typically associated with your domain wall resonance. And your ferrimagnetic resonance, simply because permeability is a complex property. So when you look at it as a function of frequency, you are going to have a resonance. And this and when typically in the high resistivity ferrites, where hysteresis and eddy current losses are low, the residual losses can be quite high, and this can lead to a lot of problems. And this is essentially been related to domain wall motion. Okay. Now, in case of ferrites, which in case of ferrites which operate at high amplitudes, and high amplitudes would mean anything in the excess of 10 millitesla. 10 millitesla is quite high amplitude of field, and frequencies of the order of 15 to 100, 10 to 100 kilohertz typical. Now, here the power dissipation is mainly hysteresis and eddy currents. In such application, these are the two main mechanisms of power losses in case of ferrites. Another parameter of importance for ferrites soft materials is their electrical resistivity. So, electrical resistivity is something that it depends upon type of material that you have, and typically ferrites, although have high resistivity as compared to metallic counterparts, but it is still of important, because this resistivity determines, as we discussed earlier, eddy current losses, and this could be quite significant if the resistivity is low. And typically the room temperature resistivity for ferrites lies in the range somewhere from 10 to the power minus 1 to 10 to the power 6 ohm meter. So, this is quite a lot of variation in the resistivity, and this depends upon composition, microstructure, etc. And this is many orders of magnitude higher than ferromagnetic alloys. So, in case of alloys, rho would be anywhere between, so it is typically lower than 10 to the power minus 6 ohm meter. So, you can see that there is a difference of at least a few order of magnitudes in the resistivity of these ferrites. So, definitely they are more resistive as compared to alloys, but still the resistivity is tunable by changing the composition. So, for instance, if you look at the data for nickel zinc ferrites, so if you plot it as a function of temperature, rho versus T, the rho versus T plot goes something like this. So, if you take this somewhere from 0 to 150 degrees centigrade or 100 degrees centigrade, this variation in resistivity is of the order of is about 2 to 3 orders of let us say this would be somewhere around 10 to the power 5, and this would be somewhere around 10 to the power 3 ohm meter. So, about 2 to 3 orders of magnitudes change in the resistivity is observed when you change the temperature by about 100 degrees centigrade. And the conductivity in these materials, essentially, if you remember module 3, I think, when we discussed conduction in ceramics. So, these materials typically, so you have Ni, so let us say you talk about Fe3O4. Okay. Now, Fe3O4 of course has FeO dot Fe2O3. So, you have Fe2 plus ions and you have Fe3 plus ions, and here you have site fluctuation, valence fluctuations, and this valence fluctuation gives rise to hopping of electron. So, essentially conduction in these materials, because you have mixed valence, conduction is because of hopping of carriers, and this is between the equivalent sites. So, for instance, you can have you can have this fluctuation from Fe3 plus to Fe2 plus, or back and forth. You have similarly nickel as well. Nickel can also exist in Ni2 plus and Ni3 plus state. You have manganese 3 plus to manganese 2 plus state. So, since all these D transition elements, they are susceptible to their change in the oxidation states, this carrier hopping becomes a major problem in terms of increasing the conductivity of these materials. However, you can change the conductivity of these materials by careful processing. So, processing parameters such as conductivity or resistivity. So, depending upon parameters like atmosphere, temperature, all of these etc., they give rise to changes in the microstructure and composition of the material, which lead to essentially change in the conductivity of the material. So, essentially you can control, if you for instance, if you use the atmosphere which allows the reduction of Fe3 plus to Fe2 plus, or if you use the atmosphere which promotes the oxidation of Fe2 plus to Fe3 plus, then you can control the resistivity of these materials. So, for instance, in case of nickel zinc ferrite, so let us say composition, so nickel NiZn Fe2 plus delta O4 minus X. So, you have nickel zinc ferrite, here iron is 2 plus delta, which means iron can be little bit in the excess or deficiency, which will affect the oxygen deficiency or excess, because as you know that if you change the composition of one cation, you are going to change the oxygen stoichiometry as well. So, this is a non-stoichiometric material, and this goes this shows a change in the resistivity of this material. So, when you plot the resistivity, log of resistivity ohm meter versus delta, this iron value. So, it goes through several orders of magnitude change at around 0, and so this goes to as high as 10 to the power 8, and this could be as low as 10 to the power 0 or 1. So, about 8 orders of magnitude change just by changing delta a little bit here and there. So, this could be delta about 0.4, this could be minus 0.4. So, you change the delta here and there about this boundary, and you have massive change in the conductivity of the material, and this is essentially because of you have Fe2 plus to Fe3 plus conversion here, and here you have Fe3 plus to Fe2 plus conversion here. So, here you have, so in this case it becomes your p type, and here it becomes n type, and of course oxygen vacancies also play an important role. So, here you give rise to what is called as hole, and here you give rise to what is called as electron, and they change the conductivity of these material. Of course, you have competing factors like nickel 2 plus to nickel 3 plus, and you have oxygen vacancy playing its role as well. So, combination of these effects give rise to a large change in the resistivity of this material, and this is an important point to note for these materials. Okay. You can also change the resistivity by addition of certain other atoms. So, rho can be tuned by addition of elements like cobalt, and this cobalt is something which maintains the iron in Fe3 plus state, because this Fe2 plus plus CO3 plus reaction gives rise to Fe3 plus CO2 plus. So, cobalt converts itself from CO3 plus to 2 plus and maintains the Fe3 plus and 3 plus state. So, basically any Fe2 plus which was in the material will convert back to Fe3 plus. Similarly, presence of Ni3 plus is also discouraged because of cobalt. So Ni3 plus CO2 plus will be CO3 plus Ni2 plus. So this is, so Ni prefers, in the presence of cobalt, Ni prefers to be in the state of 2 plus, and iron 3 plus state is preferred, and these factors increase the resistivity of this material. Likewise, the rate of cooling has an important effect as well on resistivity. And again, this is something which is quite important, because rate of cooling, the way you cool the material, the way you process the material, let us say you have a polycrystalline material of variety of grains. So now this is your grain, and this is your grain boundary. Now if you cool your material in such a manner so that now typically you know that grain boundary diffusion is faster. So grain boundary diffusivity, so dGV is higher than dG, which is dG is grain. So as a result, the grain boundaries get oxygenated more. So the way you cool them in the atmosphere, the grain boundaries get oxygenated more. So grain boundaries become insulating and the grains become semiconducting, and this gives rise to a behavior in which you have different regions of grain being semiconducting and different regions of grain being insulating, and this can be represented in the form of an electrical circuit which can be understood, and then you can study various electrical parameters. So for instance, hang on, next slide. Okay, so here since the grain and grain boundaries are different, you can treat them as if they are shunted capacitors connected in series. Oops. Just like we saw in dielectrics. So this will have its own impedance, this will have its own impedance. So when you have a dependence of resistivity on frequency as well, and when you plot the resistivity, it goes through some sort of frequency dependence, and also you can note down the similar effect in the form of when you plot tan delta as well, as well as the relative permittivity. So the permittivity will, let's say, goes like this, and tan delta will go like this. So so this can be basically modeled, and various contributions can be extracted by doing proper analysis of this electrical circuit. Finally, from the point of view of resistivity, you can also do addition of compounds, and the addition of compounds essentially to alter the nature of grain boundaries. And so if you add compounds like calcium oxide and silica, these calcium oxide and silica preferentially deposit at the grain boundaries, and what they do is that the silicon and calcium substitution in the ferrite lattice leads to in the regions which are in the vicinity of the grain boundary. This leads to regions in the vicinity of, so increases the insulation of the regions which are in the vicinity of the grain boundary. So it increases the overall resistivity of the material. So this is what essentially is about the properties of soft ferrites which are of interest. Another property which could be of importance is permittivity. Epsilon r. Now typically at around 1 gigahertz, the permittivity is about 10, for manganese zinc ferrites, but it can become very high if you decrease the frequency to 1 kilohertz. This can reach of the values of 10 to the power 4 to 10 to the power 5, and these are very high values, and this is essentially caused by this insulating grain boundaries in these materials. So again, the properties of certain properties are frequency dependent, certain properties are impurity dependent, certain properties are dependent upon the processing. So it's a very complicated game. So the processing of these materials plays an extremely important role. Processing and compositional tuning of these materials plays an extremely important role to tailor the properties of these materials according to your applications. And now what we will do is that we will look at some of the key properties of hard ferrites, and in the context of hard ferrites, so in the context of hard ferrites, essentially when we talk about it, is basically these are permanent magnetic materials. So which means they need to have large cohesivity. So cohesivity of these materials, they are called hard because cohesivity is typically higher than 100 to 150 kiloampere per meter, and this is very high as compared to your soft counterparts. And one of the most important use is permanent magnets. They are also used in memories where you don't want the states to be reversed. You want the material to remain magnetized until you do something deliberately, and for that you need to apply very large field, of course. And for these materials, as we discussed earlier, they have a large, if you draw the BH curve, the area under the hysteresis is very large, and they are characterized by what is called as maximum energy product. So basically BH max should be as high as possible. The important properties of these materials, the hard ferrites, are things like magnetic remnants, and magnetic remnants is essentially a property which is again a very important property. So you can say BR, and this is again a function of parameters like processing, the composition, etc. of these materials. Magnetic remnants can of course be changed by things like if you take barium hexaferrite, now if you take this material to be now there are various forms. You can make this ceramic. Now this is magnetic and isotropic material, okay, magnetically anisotropic. So your C axis, it has magnetization along C axis, large magnetization along C axis. So but however, if it is in ceramic form, then in the ceramic form it tends to be more isotropic because the grains are randomly oriented. So as a result, ceramic tends to be isotropic. But if you make it in the form of if you make it such a way so that you get oriented grains, so which leads to formation of oriented ceramics, this gives rise to more anisotropic nature. So you can have one scenario is like this, you have grains like so, you can have orientation of grains random, and in the second case you can have grain structure like this, and this can be achieved by proper processing. So for instance, if you plot the magnetic induction BR versus H, so for a polycrystalline, the behavior would be something like this, and for oriented barium hexaferrite would be like this, and this would be at least 2 or 3 times change in the properties. And then of course, another parameter is cohesivity, which is Hc. This Hc essentially Hc theoretically, or if you make it really well, then it could exceed even 1000 kiloampere per meter. However, for practical materials, it's in the low values, and this cohesivity is a function of a strong function of grain size. So when you plot it as a function of grain size, so so this varies somewhere something like this, and this achieves a maxima near about 1 to 2 micron, and this gives you values of the order of 150 kiloampere per meter, 130 to 150. And the reason it shows a maxima is because there is a close interaction of the domain size with the grain size. So the competition between domain contributions and the grain contributions, they reach a maxima at around 1 to 2 microns particle size in these materials. And so these are some of the important properties of soft ferrite, hard ferrite materials. I'll list some of the properties in a table. So for instance, if you look at now soft materials first, so let's say we take example of manganese zinc ferrite, and we take nickel zinc ferrite, and we compare this with something like Fe silicon, 4% silicon alloy. And so for such materials, the permeability of these materials is of importance. So for manganese zinc ferrite, it could be anywhere between 500 to 10,000. For nickel zinc, it could be anywhere between 20 to 2000 or 50 to 2000, and for iron silicon, it could be somewhere around 1500 to 2000. And the value of Hc, which is in ampere per meter, it could be for iron silicon roughly about 25-30. For nickel zinc, it could be anywhere between iron silicon would be about 30-40 here, and manganese zinc could be anywhere below 100, and for nickel zinc it's rather higher, so it would be somewhere like 25 to 1500. These are not sacrosanct values, but somewhere around these, and this is close function of doping and processing and etc. And if you look at the BS value, which is in Tesla, BS value for manganese zinc ferrite would be somewhere around 0.3 to 0.5. For manganese zinc, it would be somewhere around 0.2 to 0.4, and for iron 4% silicon, it would be around 1.9 to 2. And Tc of these temperature in degree centigrade would be it's less than 280 degrees centigrade for manganese zinc ferrite, less than 500 degrees centigrade for nickel zinc ferrite, and around 690 degrees centigrade for iron silicon. And these Tc's will again depend upon the temperature and composition and of these materials. So this is about soft magnetic materials. If we talk about hard magnetic materials, basically ceramics essentially, and then we talk about barium ferrite, typically barium ferrite. So in first case we take isotropic, and then we take anisotropic and compare with something like carbon steel. Okay, so isotropic, the values we can compare are of the Hc, which is ampere per meter, Bs, which is in Tesla, and Tc, which is in degree centigrade. So we are talking of the parameters which are of interest to these materials. So isotropic barium ferrite shows a Hc of about 200 approximately, Bs of roughly 0.3, and Tc of about 450. Anisotropic shows value of about 320, and this is about 0.4 to 0.5, and this would be a roughly, this would be 450, similar. And carbon steel, you will have about 1.6, very low, sorry, about 4 to 5, so 4 to 5, and this would be a roughly 1, and this would be 770. So you can compare the properties of hard magnetic ceramics like barium ferrite with respect to something a ferromagnetic alloy, which is carbon steel. You can also look at some neodymium based magnets like Nd, iron, and boron. These are also permanent magnets. So here the values are 58 to 60, and this would be about 1.3 to 1.4, and this would be about 160. So this is a comparison between these properties, but you can see that these properties are significantly different from what you got for soft magnetic materials. And the applications of these materials, they are used in variety of applications. So I'll not go through the details of the applications, rather I'll just list the applications which you can go through and in any standard book. So the applications of these magnetic ceramics. Now they are used in, as I said, they are used in your as inductors, cores in transformers, etc., and electromagnets. And here basically you use soft ferrites like nickel zinc and manganese zinc ferrites, and the frequency ranges are about 100 kilohertz to 100 megahertz. These are the frequency ranges, and essentially they have high electrical resistivity, which results in low eddy current losses, and they're also used in power transformers, etc. They are also used for electric equipment shielding, and this is essentially because of their high impedance at high frequency currents. So these basically prevent the high frequency, shield the high frequency noise. Another application which is important for these is data storage, and in case of data storage, essentially you use gamma iron oxide. So you use the elongated particles of these gamma iron oxide in a non-magnetic binder, and basically it's like a composite alloy, and these essentially the size is such that each particle acts as a single domain, and this single domain has their major axis in the plane of the tape. So this shows quite large magnetization, and coercive field in this form can be as high as about 100 to 200 kilo ampere per meter. So used so gamma iron oxide with a binder in the magnetic discs, magnetic tapes, essentially. Okay, and last but not the least, another application which is important for these materials, they are used as absorbing materials. So you can say radar absorbing materials. So they can be used as coatings or on top of equipments to absorb the radar signal, and they are also used for microwave applications. because of their usefulness in the frequency range from 1 to 300 gigahertz, which is a few centimeter to a meter. So, and here you use things like magnesium ferrites and garnets, etc., lithium doped ferrites for these applications. So, this is where we close this module. So, in this module what we learnt is essentially the basics of magnetism. We looked at the atomic level of reasons for magnetism, which essentially arises from your orbital and spring magnetic moment, ignoring the nuclear magnetic moment, and the sum of these two is responsible for the overall magnetism in the material. There are four kinds of various magnetisms. You have diamagnetism, which is essentially because of negative magnetization, because of Faraday's law, and essentially the magnetization induced or magnetic moment induced is opposes the applied field, and this is an effect which is present in all the materials. So, essentially all the materials are diamagnetic. It is just that paramagnetic, ferromagnetic, ferri and antiferromagnetic have extra additions which overshadow the diamagnetic additions. So, for diamagnetic materials you have susceptibility which is negative for purely diamagnetic, but for other materials susceptibility is positive, and depending upon the magnitude of susceptibility you define them in the category of paramagnet, ferromagnet, ferrimagnet, antiferromagnet. And then even in these you have different categories. Paramagnetic materials are materials where you have atoms with permanent magnetic moment, which are randomly oriented with respect to each other because of thermal forces. However, in the ferromagnetic materials and ferrimagnetic and antiferromagnetic, you have a spontaneous alignment of spins in the regions called as domains with respect to each other. The parallel alignment because of exchange interaction gives rise to ferromagnetism, and anti-parallel alignment gives rise to antiferro or ferrimagnetism. And from the application point of view, what is important is the ferromagnetic and ferrimagnetic materials, because they have remnant magnetization and cohesivity, and depending upon the area of this BH curve or MH curve, you can define them into soft and hard materials. And then we discuss the various properties which are of interest in variety of applications. The important thing to remember, the important thing which differentiates these different materials and different effects is the susceptibility and magnetization and the way they vary with temperature. In case of paramagnetic materials you have a Curie like behavior, so it decreases. In diamagnetic materials of course you do not have a temperature dependence. In paramagnetic material the susceptibility essentially decreases to 0 at temperature Tc, which is Curie temperature. In ferromagnets the magnetization drops to 0 at Tc, and susceptibility also drops to 0 at Tc, but inverse susceptibility drops to Tc temperature Tc, but the behavior is slightly different near Tc because you have this Curie-Weiss law coming to picture. So, you have slight deviation of magnetization at Tc, and then it slowly dies off to at theta. And then you of course have antiferromagnetic materials which have Neal transition, and above Neal transition they are paramagnetic, below Neal transition they are antiferromagnetic. So, this is sort of summary of this module. This will be so I have subscribed some books for you. You can read books by Principles of Electronic Ceramics by Hench and West, and then Electroceramics by Moulson and Herbert. Both are Wiley publications. So, these two books will provide a good overview, will provide you a good overview about the fundamental understanding and the applications of these magnetic ceramics. So, this module stops here. In the next module, we will start our discussion on some exotic kind of materials, electroceramics, which are superconducting materials, as well as followed by multiferroic and magnetoelectric materials, and then finally we will look at how these materials can be made. So, that is the end of this module. Thank you.